Morning and welcome to another session of refrigeration air conditioning. And my name is Dr. Mohammed Shamul Haq, and today we are going to discuss clearance volumetric efficiency and actual volumetric efficiency. Last time we discussed different types of compressor and their range of handling the volume flow rate and their refrigerating capacity. So based on that you can pick up the right type of compressor that is needed, and different types of compressor and their working. And I showed you a couple of videos regarding that so that you can understand how does the compressor function and to understand different components of it, different parts of it. So today the focus is to drive an equation for the clearance volumetric efficiency and actual volumetric efficiency, and then look at an example problem for that. So let's get started. So this is the sequence of operation for a reciprocating compressor. So intake is between D and A. If you look up this diagram, between D to A is the intake, when the intake valve will open and the fresh refrigerant or gas will enter. So from D to A, the intake valve opens at pressure P1 or just slightly below P1, and then the compression process starting at maximum cylinder volume point A. So this point A is the maximum cylinder volume. So after your piston has moved up to this point, it will start compressing it and its pressure will start rising. As the volume decreases, the pressure rises until it reaches P2 at B. So it will keep on compressing it with you can say polynomial equation PV to the power n is equal to C, the compression process, and then it will reach at point B, which is at pressure P2, and then the outlet, the discharge valve does not open until the pressure in the cylinder exceeds P2. So this outlet valve will not open till it has reached above P2, because it is set, the outlet valve is set with the spring load, and then this pressure, the outlet pressure, has to be slightly above that. Then the spring will let open the outlet port and your refrigerant can discharge from there. The discharge valve does not open until the pressure in the cylinder exceeds P2 by enough to overcome the valve spring force. Okay, so B to C is the outlet one. There we go, from B to C. B to C is the outlet pressure. So discharge between B and C, gas flows out. Between B and C the gas flows out at a pressure higher than P2 by the amount of the pressure lost through the valve at C. C is basically your outlet valve. The point of minimum volume, the discharge valve is closed by its spring. So when it reaches to a minimum volume, then this discharge port will be closed. When it reaches this minimum volume, the volume from C to this vertical line, the pressure line, is the clearance volume. So when it reaches here at point C, the outlet valve will close. Okay. Expansion from C to D. As the volume increases, the gas remaining in the clearance volume expands and its pressure falls. So as the piston is moving backward, okay, intake valve is still closed, but the gas or the vapor which was into the inside the clearance volume, it will expand that volume. So from C to D, that the fresh gas is not coming yet, but whatever was trapped in the clearance volume, that is the one which is expanding. So from C to D, as the volume increases, that is volume of the cylinder increases, the gas remaining in the clearance volume expands and its pressure falls. So as the piston is moving backward inside the cylinder, the pressure is dropping. So first the gas which is trapped in the clearance volume, that will expand, and after that, then because the pressure has dropped enough, this intake valve will open and fresh gas will come in. The suction valve does not open until the pressure falls sufficiently below P1 to overcome this spring force. So after that, this after it has fallen enough, then the spring force will let open the inlet valve and fresh gas will come in. So that's the process, entire process of a reciprocating compressor. I would like to show you a video also that will make it further clear to you, but I want you to pay attention to this clearance volume and the gas trapped into it, because that's what we will explain in volumetric efficiency, clearance volumetric efficiency. Okay, so let's go to look at the video.
A reciprocating compressor compresses refrigerant vapor in a cylinder using a piston. In a way, reciprocating compressors are like automobile engines. The pistons are directly driven through a wrist pin and connecting rod from a crankshaft. Depending on their size, reciprocating compressors may have one or more cylinders. Multiple cylinders may be arranged in line, opposed, or in a V. In each cylinder, reciprocating compressors have both a suction valve and a discharge valve. These valves give the compressor its ability to pump refrigerant vapor against a pressure difference. They are usually located in the head of the cylinder, in passages connected to the high or low pressure side of the system. Let's follow the compression process in a single-cylinder reciprocating compressor during one complete revolution of the crankshaft. Starting with the piston at the top of its stroke, or at top dead center, the piston begins to move downward as the crankshaft rotates. Because both valves are closed, the downward moving piston reduces the pressure in the cylinder. As the pressure in the cylinder falls below the low side pressure in the suction line, the pressure difference opens the suction valve, letting refrigerant vapor flow into the cylinder. The piston continues down and pulls in more vapor until the cylinder is filled with low-pressure vapor at the bottom of its stroke. Once past bottom dead center, the piston begins its upward stroke. The suction valve closes. As the piston moves up, it reduces the volume of the space in the cylinder, increasing the pressure of the vapor. When the pressure in the cylinder exceeds the high side pressure in the discharge line, the pressure difference pushes the discharge valve open, letting the compressed vapor flow out of the cylinder. This continues until the piston reaches the top of its stroke and most of the compressed vapor has been expelled into the discharge line. When the piston begins its downward stroke, the discharge valve closes. The complete cycle then repeats during each revolution of the crankshaft. This is the mechanical positive displacement vapor compression cycle using a reciprocating compressor.
So you looked at the video, and here is the process diagram with the chart of the piston cylinder arrangement here, with the schematic of the piston cylinder arrangement here. So this is the PV diagram, the process diagram for reciprocating compressor, and this is the schematic of a piston and cylinder with the head which has the intake valve and the exhaust valve in it. So the indicator diagram for reciprocating compressor is shown on the right. So this is the diagram. The vapor is compressed from A to state B. from A to B the vapor is compressed as the piston is moving in this direction, so then it will be compressed from A to B. B is basically the top dead center, A is the bottom dead center, so from A to B it will be compressed. B to C is the exhaust process, so B to C, the gas which is compressed, it will be exhausted, exhaust will be let out from here. But this, the dash line is showing the clearance volume, so the piston can reach up to this dash line, it cannot go beyond that, because if it does then it will hit the valves and it will damage your compressor. So we don't want the piston to hit the head of it or the valves which is in front of it. So this much volume has to be left. So this is called clearance volume, and from top dead center to bottom dead center or vice versa, the volume sucked by the cylinder is called the sucked volume. Okay, so from A to B the gas has been compressed, and from B to C is the exhaust, and from C to D it is the expansion of the gas which is trapped into the clearance volume. After that the pressure inside the cylinder drops enough, and then the intake valve will open and further gas will come in. So the actual volume of the gas which is being compressed and the volume of the fresh gas which has been taken in are different. It is not the same as the swept volume, because swept volume must include some portion of it which was the trapped gas which is expanded. So that's the difference between the swept volume and the actual compressed volume. The gas remaining in the clearance volume BC expands from state C to state D. So BC is the volume of the gas which is trapped, and then it will expand from C to D, from state C to state D. Clearance volume is a small space left between the cylinder head and the piston to accommodate the valves and to care of thermal expansion and machining tolerance. So this gap has to be left there because of the tolerance, because of the machining limitation, and because of these valves also. So that's why it is necessary to leave this much clearance volume here. D to A is the intake process, which commences once the vapor in the clearance volume has been expanded to state D at the suction pressure. So actually suction is starting for the fresh gas is between D to A. It is not the entire swept volume. Swept volume is from this dash line to A. The piston swept volume, this L is the stroke, and the volume covered by the stroke is called by one stroke is called the swept volume. So that volume and the volume of the gas which is being intaken is different. A to D is the intake process. Okay. Alright, so now we want to drive an equation for the clearance volumetric efficiency and actual volumetric efficiency. So we define a term clearance ratio which is denoted by epsilon. So we first want to define this term, the clearance ratio, okay, which is represented by the symbol epsilon. So epsilon is BC divided by BA minus BC. So BC is the clearance volume, this volume here, the small volume which is left above the piston head just before the valves. So that is the minimum volume inside the cylinder, divided by VA minus BC. VA minus BC is the swept volume. Okay, so that ratio we call clearance ratio. So clearance volume divided by swept volume is the clearance ratio, and we can also write it as VA minus BC is VC divided by epsilon. We are going to use it in the equation somewhere. So the clearance volumetric efficiency by definition is actual volume of the refrigerant compressed divided by the swept volume of the compressor. So the swept volume is the entire this volume up to the L, and actual volume of the refrigerant which will be compressed will be less than that, because it will be D to A. So VA minus VD, VA minus VD is the actual volume of the refrigerant which will be compressed. okay, not V A minus BC, not that one, because this much up to D, it is the previous gas which was trapped here has expanded, so we are not going to consider that. Divided by VA minus VA minus VC, which is the swap volume. Okay, so we can also write it by adding subtracting VC. Okay, so add and subtract VC, so we can get this term here. So VA minus VC plus VC minus VD divided by VA minus VC. So this thing can be simplified as 1 plus VC minus VD divided by VA minus VC, or this VA minus VC is VC upon epsilon, so 1 upon VA minus VC will be epsilon upon VC, so that's what we have replaced here. So 1 plus this term has been replaced by epsilon upon VC, so epsilon upon VC. We can do further simplification, so it will be 1 plus epsilon, so VC and VC will give you 1 VC minus VD upon VC, minus VD upon VC, and this is simply from going from total volume to specific volume. 1 plus epsilon minus epsilon, the displacement volume, divided by the clearance volume, not the displacement volume. VD is not VD, VC minus VD. VC minus VD, sorry, what is VD? VD is this expanded volume after the expansion. So VD upon VC, clearance volume divided by this volume, is the ratio here. So that is the equation for volumetric efficiency. It's a theoretical efficiency, so it does not consider any losses, doesn't include any losses. But in actual volumetric efficiency, we consider losses also, losses due to the leakage, of course, because there will be some piston ring here, so some of the refrigerant can escape that, and there are also losses due to from the valves also. There could be some loss as when the valve is closing or when the valve is opening, or simply from the sealing of the valve, there could be some losses there. So all those losses can be considered in the actual volumetric efficiency. So actual volumetric efficiency is defined as volume flow rate entering the compressor divided by the compressor displacement rate. So as the piston is moving, displacement rate will be this, as the piston is moving back and forth. So as the piston is moving back and forth, it is not necessary that every time it will get the same swept volume here. There can be some leakages from the piston ring, so this amount could be different, and the volume flow rate could be different because of the piston, the valves opening and closing, and some leakages from there. So the swept volume, the rate of the compressor displacement rate, the compressor displacement rate in terms of volume, V dot SW. So pi by 4d square will be the cross-sectional area of the piston. D is the bore of the cylinder, so D is the dia of the cylinder, and L is the stroke. So L is the stroke, and D is the dia inside this cylinder. So pi by 4d square is that cross-sectional area multiplied by the length, so that will give you this displacement volume, and then we multiply it with the number of cylinders. N, small n is the number of cylinders, and then the capital N, which is the number of revolution per second, and is the rotational speed of the compressor. So if it is one rotation, then N will be 1, so piston bend up and down one time, and if it is a 4-cylinder or if it's a 2-cylinder, then N will be two numbers, so that volume has been displaced that many times. So as it says here, where N is the number of cylinders, small n is the number of cylinders, capital N is the rotational speed of compressor in revolutions per second. So normally sometimes in the numerical it is given as RPM, revolution per minute, so you have to keep an eye on that so that you can change it to revolution per second. And D is the bore of the cylinder, L is the stroke of the length. Some of the terms you have already learned it in IC engine or heat engine, when we discussed heat engine thermodynamics. So some of these terms you are already familiar with. So V, eta VA is always less than eta Vc. Why is that? Because eta Vc is a theoretical efficiency, it doesn't consider any losses, and eta Va is the actual efficiency, it is considering the leakages and pressure losses and other stuffs too. So that's why Va will always be less than Vc. Due to the pressure drop across suction and discharge valves, leakage past piston rings, leakage back through the discharge and suction valves, and cylinder heating of the suction gas. So the isentropic compression efficiency, or simply compression efficiency, eta C, is the isentropic work of compression divided by actual work of the compression. So this is the same isentropic efficiency that we have discussed earlier in thermodynamics. We'll look up, we will see this thing in the example problem also. So I hope this equation is clear and you can understand this. So now I want to move on to look at one simple numerical on this thing. Here is that numerical. As you can see, the example numerical reads as the catalog of for a refrigerant 22 4 cylinder. So 4 cylinder means the small n is 4 and the refrigerant is 22, so we have to use 22 charts and tables. Hermetic compressor operating at 29 revolution per second, so it's already given in rotation per second, so revolution per second. Condensing temperature of 40 degrees centigrade and evaporating temperature of minus 40 centigrade. The condenser is at 40 degrees centigrade right here, and the evaporator is minus 4 degrees centigrade. Shows the refrigerating capacity of 150 kilowatts, so we are getting from the evaporator 115 kilowatt. At this operating point, the motor whose efficiency is 90%, so eta M is given as 90%, draws 34.5 kilowatt of power. The bore of the cylinder is 87 millimeter and the piston stroke is 70 millimeter. So bore and strokes are given, so we can calculate how much is the swept volume. The performance data are based on 8 degrees centigrade of subcooling. So instead of when the condenser is cooling the refrigerant, it doesn't stop at the saturation saturation liquid line. Instead it goes into the subcooling, and the subcooling is of 8 degree. So if this is the 40 degree temperature line, then the subcooling is going up to 32 degree. 32 degrees on the temperature line. The temperature line goes from here all the way here and then this way, as you have known it before. Compute A, the actual volumetric efficiency, and B, the compression efficiency. So actual and isentropic efficiency, that's what we need to calculate. So compressor data, N is 4, N is the number of cylinder, 4 cylinder, N is the rotation per second or revolution per second, which is 29, D is the diameter of the cylinder, which is 87 millimeter bore, and stroke is 70 millimeter. So eta motor is given as 90% or 0.9. W motor, the motor power is 34.5. The motor is drawing a power of 34.5 kilowatt. So we can find the H1, which is set at the saturation point. So we can look up the saturation table for refrigerant 22 and find out what is H enthalpy here and the specific volume here. So I have copied that table right here, as you can see. So as you can see, H1, which is Hg at 40 degrees at minus 4. So it's minus 4. It is minus 4 right here, and Hg will be 403 here. So 403, right, this amount 403. So I've written down that one. And the specific volume at the inlet of the compressor is V1, and V1 is 0.053 right here. So V1 is 0.053 right here. So I have done these two values right here, meter cube per kilogram. Okay. Then S1, the entropy at point 1 is 1.7566, 1.7566. So I wrote it down, kilojoule per kilogram Kelvin. Okay, written down that one. Why do we need that? We need it because 1 to 2 is a constant entropy process. So when we draw it, because we need H2 also. H2 is in the superheated region. We cannot find it from the saturation table. We have to find it from the superheated table, or we have to use the chart. So here I am going to use the chart. So I will show you how. I will draw this diagram on the chart and then read this value, H2 value. So when we read it, it will be like so state 2 is obtained at intersection of constant entropy line drawn from state 1 at constant pressure line at 40 degrees centigrade. So this constant entropy line, we will start from point 1 and it will keep on extending till it hits the 40 degree line. So when it touches the 40 degree line or 40 degree the condenser pressure line, constant pressure line from condenser. So there it will be the H2 amount. From there we will read it in the bottom here. That will give us the H2 424. So and this is 32 degree after the subcooling. So if we have to find out what is H3, so T3 will be 40 minus 8, 32 degree centigrade, and H3 will be HF at T3. So HF at T3 a fluid is 239.19. 239.19 right here. So that's why I have written this 32 degree table also from there, 239.19. So and the H4 will be same. Okay, H4 is equal to H3. Alright. So the actual volumetric efficiency is volume flow rate entering the compressor, m dot V1 divided by compressor displacement rate. So which is pi by 4d square into L into N into N. Okay. So this will give us the volume flow rate. We know V1 right here. We found that out, but we need to calculate m dot, the mass flow rate. When we multiply mass flow rate with the specific volume, it will give you the volume flow rate. V dot, it will give you the capital V dot. The volume flow rate divided by the swept volume or the displacement rate. Okay, that will be the actual volumetric efficiency. So to figure out what is the M value, we have been given the refrigerating capacity 115, and if we can find out so we know H4, we know H1, so H1 minus H4 into m dot is equal to the refrigerating capacity, this one. So this one is given, we can, and H1 and H4 we found out from the table, so we can find out what is the m dot. So let's look at right here. So Q dot L is the refrigerating capacity, is m dot H2 minus H1. So replacing all the values here, this is 115 and these two values we have jotted down. So you can calculate that m dot is equal to 0.7 kilojoule per second. Okay, that's the mass flow rate. And inserting the values in the above equation, we get eta VA as 0.776 or 77.6%. That's the actual efficiency. The isentropic efficiency is isentropic work divided by the actual work. Isentropic work is m dot H2 minus the compressor work and the ideal compressor work, because it is we are considering compressor to be isentropic. So work done, isentropic work done divided by the actual work done. So actual work done, because we know how much watt power motor is consuming and what is the motor efficiency, so we can find out what is the actual work. So if you multiply that one, you will get 68.6%. So I hope you understand. I want to show you how to read value H2 from the R22 graph. This is the R22 graph, okay, and This is our evaporator line at minus 4 degrees centigrade, approximately minus 4. The green line is at minus 4 degree centigrade saturation pressure. Okay, and then this red line is the condenser line at 40 degrees centigrade. So these are the two lines. So point 1 is at the saturation line, saturation vapor line, this curve, and where the evaporator line is crossing each other. So this is point 1, and the entropy, which is between 1.7 and 1.8, we have read it from the table as 1.75. We have read it from the table as 1.75. So we are going to take that as constant, draw a parallel line between 1.7 and 1.8, and wherever it crosses the red line, which is the condenser line, that will be your point 2. From there you have to draw the vertical line downward, then you have to read this value. This is the H2 value, which is 434 I have taken. So this I have taken as 434, this value right here. You have to practice a little bit so you can read it right here. Right. So that's about it. The only thing I want to tell you is the subcooling. Subcooling was 8 degrees. So here on this graph you have temperature lines like this gray line that I have. These are all the temperature lines, starting from here, like say 10 degree, 20 degree, 30 degree, 40, 50, like that. So it says it has a subcooling of 8 degree. That means the condenser was actually at 40 degree, and then subcooling is done 8 degree further, so it will be going 32 degree. So I have drawn this 32 degree line here, this line here. This is the 32 degree line. Let me highlight it, this one. This one is the 32 degree line right here. So it crosses your condenser line at this point. So point 3 is right here inside the subcooled region, and 3 dash is on the saturation point. So you can read H3 value. I have read it from the table. You can also read it right from here. So you will see it is below 250 but more than 200. So if you read it accurately, you will get 234. 200 how much I took? H3 I have taken. Where is H3? H3 I have taken as 239. So that's what there. Okay. So that will conclude our discussion. I hope you understand, and if you have any question, please mark it with this slide number so we can go over it during our live session. I thank you once again, and I will tell you that you should be looking for and have all your tables and everything ready, so that when we are on live session will be a very short time. It's not too much time there. So you have to be, and all of you are together during the live session. So a lot of you might have questions. So if you have it, and I have also posted all these slides on your Google Classroom. All these slides are there. So you can go over it again. You can watch the video. You can look at the actual slides and see if you have any questions. If you have any questions, mark it with the slide number. If you tell me this slide and this is what I'm not understanding, then I will try my best to explain you that one. So that should be it for today, and inshallah we'll meet again.